As shown in this schematic conceptual image, simple inchworm robot can explore narrow space such as pipes and drains. Because the mechanism and structure of the body of the inchworm robot is quite simple, it is suitable to be adapted to pipes and drains with different shapes of cross-sections. This is the schematic image of the double network gel, DN gel, on the leg of the inchworm robot. When current flows through the circuit, the molecule of water emerges around the cathode that is attached to the right surface of double network gel. This water reduces the frictional resistance of a leg of the inchworm robot, and this leg works as the lifted leg of the inchworm robot. After current stops, the water vaporizes from the cathode of the circuit, and frictional resistance of the leg is also recovered. This is how the leg returns to work as supporting leg of the inchworm robot. In this study, DN gel was manufactured by Professor Hidemitsu Furukawa and Professor Kazunari Yoshida at Yamagata University in Japan. This video shows the fundamental motion of the first inchworm robot with rectangle blocks of DN gel at the bottom of its two legs. This robot was designed and manufactured by Mr. Minoru Takagi and Professor Riichiro Tadakuma at Yamagata University in Japan. As the linear actuator to expand and shrink the body of this inchworm robot, two lead screws were used at its front and back parts. The metallic plate at the bottom of the inchworm robot works as the cathode of the electrical circuit to activate the DN gel. When one leg works as the lifted leg with the current flow and water that emerges around the cathode plate under the lifted leg reduces the frictional resistance. Lead screws works in orchestrated way to move the lifted leg to the target direction. After moving the lifted leg, the current on that leg stops, and the water vaporizes from the cathode plate at its bottom, so the frictional resistance of the leg is also recovered. Now, this leg can be used as a supporting leg with large enough frictional resistance. After that, the other leg works as the lifted leg with the current flow on its DN gel to reduce its frictional resistance. By repeating this process multiple times, this inchworm robot can continue to move forward and backward smoothly on the metallic plate as the cathode. To realize the flexible inchworm robot to move in narrow space, shape memory alloys were adapted as the linear actuators instead of lead screws used for the first prototype. By using shape memory alloys to expand and shrink the body of the inchworm robot, its flexibility can be much improved, and its total size and weight can be also reduced. This is the second prototype of the inchworm robot that has flexible body composed of shape memory alloys and DN gels. As the linear actuators to expand and shrink the body of this inchworm robot, multiple shape memory alloys were used at its first and second segments. The metallic plate at the bottom of the inchworm robot works as the cathode of the electrical circuit to activate the DN gel just like the first prototype. When one leg works as the lifted leg with the current flow, and water that emerges around the cathode plate under the lifted leg reduces the frictional resistance, shape memory alloys works in orchestrated way to move the lifted leg forward. After moving the lifted leg, the current on that leg stops, and the water vaporizes from the cathode plate at its bottom, so the frictional resistance of the leg is also recovered. Now this leg can be used as a supporting leg with large enough frictional resistance. After that, next leg works as the lifted leg with the current flow on its DN gel to reduce its frictional resistance. By repeating this process multiple times, this inchworm robot can continue to move forward smoothly on the metallic plate as the cathode. The flexible circuit at the top of the robot was designed and fabricated by Professor Hiroyuki Matsui at Yamagata University in Japan. To move in arbitrary environment freely, we decided to deploy the cathode on the leg of the third prototype of the inchworm robot. This video shows the physical principle of the walking motion of the third prototype of the inchworm robot. When the left leg works as the lifted leg with the current flow and water that emerges around the cathode of the left leg, the shape memory alloy that is connected to the left leg also shrinks with the current flow, and it pulls this left lifted leg. In this video, the electrodes with current flow are yellow, and the shape memory alloy activated with current flow is red. The DN gel with current flow that provides water to reduce frictional resistance is blue. After pulling the lifted leg, the shape memory alloy cools down with cutting the current, and it expands and pushes the second leg in the middle that works as the lifted leg with current flow this time. The right shape memory alloy shrinks at the same time with current flow, and it pulls the second leg at the middle of the robot's body with small frictional resistance. After moving forward, the middle leg returns to the supporting leg by cutting the current, and the shape memory alloy also starts to expand by cutting its current. For the while, the right leg works as the lifted leg with current flow, and small frictional resistance with the water emerges around its cathode. So the right leg moves forward while it is pushed by the expanding shape memory alloy on the right side. By repeating this process multiple times, this inchworm robot can continue to move forward smoothly with very simple mechanism. This is the real motion of the third prototype of the soft inchworm robot with 2 segments. By switching the lifted leg and the supporting leg with current flow, the robot can move forward smoothly in a narrow pipe. Because the anode and the cathode was deployed on the leg together, the metallic plates at the bottom of the first and second prototypes of the robots were not needed this time. The bellows structure was adapted to the segments of the inchworm robot to follow linear motions of the shape memory alloys smoothly. The similar design was also adapted to the flexible inchworm robot developed by Mr. Moses Gladson at Yamagata University in Japan.